Model-based reinforcement learning algorithms can attain significant sample efficiency, but require a proper network structure to represent system dynamics. Current approaches include white box and black box modeling, but they suffer from a bias-variance trade-off in the learning process. As an alternative, gray box modeling leverages prior knowledge in neural network training, but only for simple systems. In this paper, we devise a nested mixture of experts for representing and learning complex robotic systems, including hybrid systems. The top layer forms a competitive NMOE with M local experts and the gating network. As a nested structure, top layer's local experts form a cooperative NMOE containing two local experts and a gating network. We define a loss function so that the local experts in the top layer are trained to compete with each other, whereas the two local experts in the bottom layer are trained to cooperate. Thanks to this novel structure, our NMOE provides a general method to incorporate various types of prior knowledge. To be more specific, we consider information on physical contacts between a system and an environment, which is incorporated into the top layer. We also consider robots' kinematic structures and dynamic properties, which is embraced in the bottom layer. HalfCheetah, for example, we roughly estimate that the robot makes rigid contact with the ground, yielding 4 different contact moves. Consequently, we define a competitive NMOE with 4 local experts associated with front foot contact mode, rear foot contact mode, front and rear foot contact mode, and contact-free mode. Note that the gating network divides input data into 4 subsets and assigns them to local experts associated with the contact modes. As a nested structure, each local expert associated with the contact modes is formulated with another mixture of experts. It is composed of the black box model, which is multi-layer perceptron, and the white box model based on the first principles. The gating network combines the output from the black box and the white box model based on the accuracy of the prior knowledge. Here, the white box model provides a reasonable initial representation of the system and enables quick convergence of the learning process with low variance. In contrast, the black box model eliminates the residual errors left by the hard-to-model effects and reduces the bias. In the experiment, we evaluate our NMOE framework using various continuous control domains. This experiment shows that our method successfully outperforms related baseline methods in terms of data efficiency, generalization to unseen data, and bias variance trade-off. We evaluate the gating network in the competitive NMOE using cart-width elastic wall domain. The phase plot demonstrates that the NMOE successfully assigns input data, which have negative displacement and negative velocity, where the cart is most likely contacting with the elastic wall, to the first cooperative NMOE. Similarly, the NMOE successfully assigns inputs to the second cooperative NMOE when the cart is in contact-free mode. We further evaluate the gating network in the cooperative NMOE using richer domain. The table shows that the NMOE relies more on the white box model to generate the output when the prior knowledge is more reliable. Finally, we evaluate our NMOE using an MBRL setup, where the network is linked to a model-based controller and is trained online. It shows our method provides reliable model accuracy for the controller more efficiently than the related baselines and achieves the best final performance after converge. Here, we show HalfCheetah test. After 3K time steps, our NMOE framework is able to learn a model, provide reliable prediction to the controller, and achieve running behavior quickly compared to the baseline method.